The process begins with high-quality special steel, chosen for its ability to withstand harsh mining environments. The steel arrives in 8-meter-long rods, which are then cut into 33-centimeter segments. Each of these segments will eventually form a single chain link. Once cut, the steel segments are heated in an induction furnace to 1,250 degrees Celsius. At this extreme temperature, the metal becomes malleable enough for shaping. The glowing steel rings are then placed under a hydraulic press, which applies 200 tons of pressure to forge them into flat links. These flat links are a key component of mining chains, providing strength and stability. Next, the pre-cut steel bars are heated to around 600 degrees Celsius and bent into shape. A welding machine then fuses the ends of each link together, ensuring a strong connection. During welding, sparks fly to expel impurities and prevent oxygen from contaminating the weld, which could weaken the structure. This step is crucial for maintaining the chain's integrity. The individual links are assembled in a carousel production system, where they are combined into a continuous chain. The process follows a pattern: a flat link, then a round link, then another flat link, ensuring uniform strength and flexibility. This assembly is carried out by both machines and skilled workers. Mining chains are typically produced in 100-meter lengths, weighing approximately 3.6 tons. However, the factory can also manufacture custom sizes based on specific customer requirements. The process begins with selecting high-quality steel or alloy, which is then processed into wire or sheet form. The material undergoes cutting, shaping, and surface treatment to enhance its strength and resistance to wear. In this stage, chain plates are cut from high-strength steel sheets using precision stamping or punching machines. The process involves high-pressure dies that shape the plates and create pinholes with exact dimensions. Accurate punching ensures uniformity, proper fit, and smooth articulation of the chain. Any burrs or rough edges are removed to prevent premature wear. Heat treatment. Shot peening. During chain assembly, individual components, plates, pins, rollers, and bushings are precisely aligned and pressed together using automated or semi-automated machinery. The pins are riveted or press-fitted to ensure secure connections. Proper lubrication is applied to reduce friction and wear. This step ensures the chain moves smoothly and maintains durability under operational loads. The assembled chain undergoes rigorous testing to ensure quality. Breaking load testing verifies the chain's maximum tensile strength, while length testing ensures dimensional accuracy. The Eefde-Lock, a crucial waterway structure in the Netherlands, experienced a major mechanical failure on January 3, 2012, when one of its gates unexpectedly fell. Upon analysis, experts discovered that the gate's fall was due to a structural defect in the attachment of the hoisting chains to the lock gate. The defect led to a sudden and complete loss of tension in the chains, which caused them to snap. Since the hoisting chains play a vital role in lifting and securing the lock gate, their failure rendered the lock inoperative. The damage not only disrupted normal operations, but also raised concerns about the overall integrity of the lock's mechanical components. Given the lock's significance for inland navigation, swift action was required to replace the damaged chains and restore functionality. Under normal circumstances, the production of specialized hoisting chains, specifically the Gauls chains used in the Eefde-Lock, requires a manufacturing period of approximately 12 to 16 weeks. However, due to the urgent nature of the situation, the German chain manufacturer Kobo was tasked with expediting production. Remarkably, Kobo managed to deliver the new chains in just 6 weeks, less than half the usual time required. This rapid response was crucial in minimizing downtime and ensuring that the lock could be brought back into operation as quickly as possible. The replacement hoisting chains were designed to meet stringent technical requirements to ensure durability and reliability. The key specifications of the new chains included total number of links per chain, 229 total number of link plates, 1,832 minimum tensile strength, 1,200 newtons per square millimeter calculated braking force, 2,200 kilonewtons length per chain, 25,510 millimeter. Total number of chains required, 4. Once the newly manufactured chains arrived, the next critical step was their installation and placement. Given the complexity of the lock system and the weight of the chains, the installation required careful planning and precise execution. The process involved removal of the broken chains. The damaged chains were carefully detached from the lock gate to avoid further damage to the structure. This required the use of heavy machinery and skilled personnel. Inspection and preparation. Engineers conducted thorough inspections of the attachment points and supporting structures to ensure that no additional weaknesses were present. Any necessary reinforcements or modifications were carried out before the new chains were installed. Positioning the new chains. Using specialized lifting equipment, the new chains were positioned and aligned with the lock gate. Proper alignment was crucial to ensure smooth operation and prevent future mechanical stress. Secure fastening and testing. The chains were securely fastened to the gate and subjected to a series of tests, including load-bearing assessments and operational simulations. These tests ensured that the new chains met safety and performance standards before the lock was brought back into full operation. Restoration of lock operations. Following the successful installation and testing of the new chains, the IFTA lock was restored to operational status. The expedited manufacturing and installation process significantly reduced downtime, preventing prolonged disruptions to maritime traffic. The incident also prompted a re-evaluation of maintenance and inspection procedures to prevent similar failures in the future. The process begins with wire drawing, where high-quality steel wire is pulled through a series of dies to reduce its diameter to the desired thickness. This step is essential for ensuring uniformity and strength while preparing the material for the subsequent forming stage. Once the wire is drawn to the appropriate size, it is cut into precise lengths and formed into interlocking chain links. Specially designed machines shape the wire into links while maintaining strict dimensional tolerances. Proper forming ensures that each link is uniform and ready for welding, contributing to the overall strength of the chain. After the links are shaped, they undergo a welding process where the ends are fused together using electric resistance welding. This method ensures a strong, seamless joint, which is critical for the chain's durability and load-bearing capacity. The welded area is carefully inspected to ensure complete fusion and prevent weak spots that could compromise the chain's integrity. To enhance the chain's strength and toughness, it is subjected to a heat treatment process. This involves controlled heating and cooling cycles that refine the chain's microstructure, improving wear resistance, tensile strength, and overall performance. Different heat treatment techniques may be used depending on the chain's intended application. Quality control is a crucial part of Campbell's chain-making process. After heat treatment, each batch of chains undergoes rigorous testing, including tensile strength tests, hardness checks, and dimensional inspections. The process begins with high-quality steel wire ranging from 3 mm to 40 mm in diameter. Depending on the required grade and strength, different manufacturing methods shape the steel into chain links. Once the links are formed, they undergo welding to create a continuous chain. Over 1 million welding processes are performed daily, ensuring secure connections between links. After welding, the chains are calibrated and tested for weld integrity, ensuring they meet stringent safety standards. The next critical step is heat treatment, which enhances the chain's strength and durability. The chains are subjected to extreme heat and cooling cycles, improving their tensile strength, wear resistance, and fatigue resistance. This process is vital for ensuring the chains can withstand demanding industrial environments. Safety and reliability are top priorities in the production process. Every chain is load tested during manufacturing, ensuring it meets or exceeds performance requirements. Random chain links are extracted and inspected since a chain is only as strong as its weakest link. Additionally, safety-critical components undergo crack detection tests before proceeding to the next stage. The process often begins at temperatures of around 1,700 degrees Celsius, where materials such as ferrochrome, ferrowolfram, and nickel are combined. These elements play an important role in the production of stainless steel. Ferrochrome is primarily used to add chromium, which imparts corrosion resistance to the steel. Nickel, on the other hand, enhances toughness and ductility. For smaller batches, a 14-ton furnace operating at 1,100 degrees Celsius is used. This furnace can melt and refine smaller quantities of steel, while maintaining strict control over temperature and material quality. The melting of smaller batches allows manufacturers to experiment with various alloys, ensuring the desired composition and properties are achieved in the final product. These mills exert up to 5,200 tons of pressure, ensuring that the steel is shaped to the required specifications. The rolling process further refines the steel and ensures uniformity, creating a product that is not only strong and durable, but also has the ideal surface finish for its intended use. Stainless steel production involves several sophisticated processes and techniques designed to create high-quality, durable materials suitable for various industrial and consumer applications. The production process starts with melting raw materials in specialized furnaces, followed by refining, alloying, and forming the steel into its final shape. Key components like ferrochrome, ferrowolfram, and nickel are often used in the production of stainless steel to enhance its properties. To ensure a high degree of purity, the melting process is performed in a vacuum or under controlled conditions. Desulfurization, deoxygenation, and gas-free conditions help eliminate impurities, ensuring the steel has superior quality. Melting under vacuum, VIM, is particularly beneficial because it helps to produce cleaner steel with fewer inclusions and lower concentrations of harmful elements. These processes contribute to the overall improvement in the mechanical properties of the stainless steel, making it more reliable for high-performance applications. Once the steel is melted and refined, it is subjected to high-pressure processing. This step typically involves a pressure of up to 1,000 bars, which allows the steel to be more compact and denser, enhancing its strength and resistance to wear and tear. The use of high pressure also aids in the removal of any remaining impurities that might affect the performance of the steel. In addition to these advanced melting and refining techniques, modern stainless steel production involves the use of cutting-edge rolling mills. The most advanced rolling mills in the world are fully automated, allowing for precise control over the rolling process. The combination of these advanced techniques, high-temperature melting, vacuum processing, high-pressure treatment, and automated rolling, ensures the production of stainless steel that boasts exceptional strength, durability, and resistance to corrosion. This makes stainless steel an essential material in industries ranging from aerospace to medical devices, automotive manufacturing, and more. Furthermore, the use of modern production technologies guarantees the longest tool life, as the final product is optimized for performance and longevity. The process begins with a large block of steel, which is heated to a high temperature in a furnace. Once sufficiently hot, the steel becomes malleable, allowing it to be shaped. A hammer is used to strike the glowing steel, transforming it into the rough shape of the anchor's shaft. This stage is crucial because the steel's properties, particularly its flexibility and strength, are developed through the forging process. The steel's flexibility is essential to ensure that the anchor can absorb shock without breaking, as cast iron would be too brittle for such demanding use. After the basic shape is formed, the anchor's individual components, such as the shaft, flukes, and other parts, are created from steel plates. The steel is cut with precision using a special high-temperature cutting burner. The burner can handle steel plates up to 40 centimeters thick, cutting through the material with ease. The ability to work with such thick steel ensures that the anchor can endure the extreme pressures and stresses exerted on it in marine environments. The next stage involves assembling the anchor's various components. Large, heavy parts such as the shaft and side elements are positioned, and workers use cranes to move and align them. To ensure the components stay securely together, they are welded using shielding gas welding techniques. This method creates strong, durable seams that are as hard as the steel itself. In addition to welding, the workers also make final adjustments using a cutting burner and place steel plates in front and behind joints to ensure a solid fit. Temporary welds are used initially, which are later reinforced for added strength. One of the critical components of the anchor is the swivel joint that connects the anchor to the chain. The swivel joint allows the anchor to move with the ship's motion without damaging the chain or the anchor itself. The anchor's swivel joint is made by preparing the anchor part and attaching a ball joint mechanism. The two parts are connected using a large nut, which is tightly fastened to prevent loosening during use. This special swivel joint ensures that the anchor can move freely, even under extreme conditions, without compromising the integrity of the entire system. The workers secure the joint by ensuring the anchor shaft tilts forward by up to 40 degrees, which is necessary for the anchor's proper function. Once the correct angle is achieved, the shaft is secured to prevent excessive tilting. To stabilize the joint further, two steel plates are placed in front and behind it. At this point, the anchor is still temporarily welded. The actual assembly begins as the workers use shielding gas welding, ensuring the seams are as strong and durable as the steel itself. Despite the anchor's impressive size, it is still not complete without the crucial swivel joint, which connects the anchor to the chain. The workers begin by preparing the anchor part of the swivel, followed by adding the chain part, which features a special ball joint. The two swivel components are then connected using a massive threaded nut, ensuring a secure fit. To prevent the nut from loosening under pressure, a worker tightens it firmly. Next, the swivel joint must be attached to the anchor shaft, a process that can only be done with the assistance of a crane due to the weight and size of the components. Once in place, the connecting bolt between the anchor and the swivel joint is welded firmly. Before the anchor is ready for use, it undergoes a stress test where a machine applies 120 tons of force to ensure its strength. With this test passed, the final step is coating the anchor with bitumen, a petroleum-based substance that is water repellent and protects the steel from corrosion due to seawater. This coating ensures the anchor's longevity and readiness for the world's oceans. The process of dropping the anchor chain on a ship is a carefully coordinated procedure to ensure the vessel stays in place. When the ship reaches the desired location to anchor, the captain gives the order to prepare the anchor system. The crew begins by unlocking the anchor chain compartment, which holds the chain and anchor. The crew then operates the windlass or capstan, which is a mechanical device used to control the release of the chain. As the windlass is engaged, the anchor chain begins to unroll and drop into the water, gradually lowering the anchor toward the seafloor. The speed at which the chain is released is monitored to ensure it is done smoothly and evenly, preventing sudden jerks or damage to the equipment. As the anchor chain continues to lower, the weight of the chain and anchor pulls the anchor down until it reaches the seabed. The anchor itself is designed to dig into the seafloor, providing a secure hold for the ship. The crew continues to let out the anchor chain until it has reached the necessary length, typically around 5 to 7 times the depth of the water. Once the anchor is fully deployed, the chain is tensioned to ensure that the ship is securely held in place. The crew then locks the windlass to prevent any further movement. The anchor is now firmly set, and the ship can remain stationary until it is ready to depart.